Let's keep going. Yeah. Next topic is the Latimer diagrams. How to find E0 for a new half reaction. Okay. Let's look at this figure. This Paul iodate. Since iodine has many oxidation state. Okay. So this kind of diagram uh, we can make, right? This is called Latimer diagrams. Okay. And display the standard reduction potential connecting various oxidation state of an element. Yeah? This is an example of iodine. For iodate, okay, and then here in this state, the iodine has hexa, oh no, hepta, positive heptavalent, okay, and then this iodate, this iodine oxidation state is +5. Here is +7, and this one, I don't know. What's the name? Let me see. Uh, hypoiodite. Okay, hypoiodous acid. Right. This one here, iodine oxidation state is +1, and iodine. This is a simple solid and 0. Okay, and then iodide. The oxidation state of iodine is -1, and this diagram tells the standard reduction potential. Okay, but here iodate can be reduced to iodide, and this electrode potential is not known, right? And question is, can we calculate this potential using other values? Okay, the answer is yes, of course. Why? Look at that. This one is unknown, okay, but here uh, iodate to iodine, yeah, this potential is known, and iodine to iodide potential is also known. So by the combination of these two, and then we can calculate iodine potential from iodate to iodide. Okay, or yeah, we can take this one, iodate to this hypoiodide to, and also to iodine and iodide. But it is one, two, three, yeah, three stages. But if we take this one, it is only takes 1 and 2 steps. Okay. Anyway, let's and consider this iodate to hypoiodous acid. Okay, and this is 1.154 volt. Yeah, that's a standard reduction potential. And although it gives this a very simplified information, but you have to, yeah, you have to write the complete this Hepser reaction. Okay, uh, let me explain very briefly. The first thing you have to do is that to uh, calculate, to know the oxidation state of iodine. Here this is +5 state. Okay, here is +1. Okay, so naturally we can say that there are 4 electrons are involved here. Okay, so iodate plus 4 electrons. All right, and then we make charge and mass balance. Okay, and here, since on the right hand side, let me see, uh, yeah, we know the number of electrons, and on the left hand side there are 3 oxygen atoms, but on the right hand side only 1. So we have to add oxygen, since this reaction takes place in water, and then we have to add water on the right hand side here. Okay, and here we added 2 water molecules. Yeah. And then what the oxygen atoms here on the right hand side there are 3, and left hand side also 3, but number of protons no doesn't is not balanced. Okay, so here on the left hand side we add protons. Okay, since on the right hand side there are 5 protons, so we add 5 protons here, and then we examine, okay, to see if this HEP reaction satisfies the charge balance and mass balance equations. Okay, let's look at the first charge balance on the left hand side. -1 plus 5 is, which is +4, and -4 and 0. Okay, and on the right hand side there is no ions. Okay, 0. All right, and let's check mass balance. On the left hand side there is only one iodine, and the right hand side only one, and there are 6 oxygen atoms, 3, I'm sorry, and on the right reaction there are 3, yeah, oxygen atoms, and the 5 hydrogen, no, on the left hand side atom, and on the right hand side also 5, yeah, so this is correct. Okay, now let's consider how to calculate the standard reduction potential from iodate to iodide. All right, and our strategy is to combine this iodate to iodine and iodine to iodide, yeah, and then we apply this gives free energy and electric potential relationship. Okay, let's first consider the reaction from iodate to iodine. Here it can be written this way, yeah? And then we calculate the Gibbs free energy change for this reaction. Delta G, let's say 1, 0 equals minus NFE, and minus how many electrons are there? 5. F is constant, and E is a standard reduction potential. It's already given here, 1.210. Okay, and then what's the this one? Iodine to iodide. Yeah, we can write it this way, and delta 2 0 equals minus n is 1, and F multiplied by the potential 0.535. Yeah? And then when we add these two HEP reactions, we get iodate to this one. Okay, plus 6 protons and plus 6 electrons is iodide plus 3 water molecules. Okay, and then this is Gibbs free energy change, in this case delta G30, okay, equals minus 6 Fn. We don't know here, yeah, standard reduction potential. This is what we want to calculate. Okay, although the electrode potential is intensive property, right? So we cannot add or subtract. But if we convert into the Gibbs free energy change, and Gibbs free energy change is a set function, so we can manipulate okay, this one. So since we added these two, and Gibbs free energy also can be added, so delta G30 equals delta G10 plus delta G20. Okay, this one holds. Why? Because Gibbs free energy change is a set function. That's very important. And what other set functions do you know? Yeah, there are many, and not many actually. There are several. For example, enthalpy change is a state function, and entropy change is also a state function. Okay, but work or heat, they are not state function. Okay? So we can set up this equation, and then E3 and 0 is given by this one, and then we get 1.098 volt. Okay, this is the answer. Okay, let's consider different descriptions of the same reaction. Okay, let's consider this reaction. Silver chloride, which is a white crystal, and it can undergo electrochemical reaction. It reacts with one electron to become silver, to produce silver metal and chloride ion. And then from the appendix, we find the electrode potential, standard electrode potential is 0.222 volts. Okay, here. Let's look at this setup. Yeah. And write Nernst equation. E plus, since this is a cathode, let's assume this is cathode, and E plus equals this one 0.222 minus n is 1, 0.05916 log, and the concentration of chloride ion. Okay, in this case, what's the chloride ion concentration? And since solution contains 0.0167 molar cadmium chloride, and it completely dissociates. Okay, the cadmium chloride species produces two chloride ion, so chloride ion concentration is twice of this value, okay, which is 0.0334. Okay, and then this cathode potential is 0.3093 volt. Okay, yeah, you understand? But here is another way to calculate this potential of a silver electrode. First, we consider silver ion now accept electrons to become a silver metal, and from the appendix we know this standard reduction potential for this reaction is 0.799 volt. Okay, and we can write this Nernst equation. But how do you consider silver chloride? Yeah, silver chloride is not very soluble, and from KSP, okay, you know the KSP for silver chloride equals silver ion concentration multiplied by chloride ion concentration. And here, instead of this silver ion concentration, we substitute this one. Okay? Silver ion concentration is given by KSP divided by chloride ion concentration, and KSP is already known, which is 1.8 times 10 to minus 10 divided by this one. Silver ion concentration, chloride ion concentration is this one, yeah? And then we get this number, yeah, this value for silver ion, and then we insert this value to here, and then we get almost identical, right? Cathode potential 0.3099 volt. There is a very small difference. That difference arises because of the uncertainties in KSP. Okay, you understand? It's a very useful, right? Yeah. Or you can consider this reaction reversibly, which means that once you know the electrode potential here, okay, the electrode potential of a silver electrode, and then we can calculate KSP, okay. But here this example shows that using KSP we can calculate this electrode potential. But once we know the electrode potential, reversely we can calculate KSP. You see, which is very useful, thing. Okay, let's consider another one. Advice for finding relevant F reactions. How to figure out the F reactions when faced with a cell drawing or line notation. First, write reduction reactions for F cell. Okay, reduction reaction. Write, yeah, in reduction form, and look in the cell for an element in two oxidation states. Okay, here let's consider this seemingly complicated reaction here. This is anode, this is cathode. Okay, and the right F cell, this is cathode, copper ion accept two electrons to become copper. And left-handed reaction. Yeah? Although this is oxidation takes place here, but we write in the reduction form this one. lead fluoride. Yeah? This one accept two electrons to become lead, the metal, and two fluoride ion. Okay, or we can choose the half reaction, the left half cell reaction, as this one. Simply lead ion accept two electrons to become a lead metal. Okay, either way, that doesn't matter actually. Right? Two half two left half reactions are equally valid. Okay, they are all valid. But if you take this half cell reaction, and then you have to consider the KSP for this lead fluoride. All right. Yeah. But here is caution: don't invent species not shown in the cell. Use what is shown in the line diagram to select the half reactions, which means that, yeah, here it contains fluoride ion, but don't write something like fluorine gas F2, because F2 it doesn't appear here. Okay, you understand? Okay, let's stop here.